Hey everyone, my name is Sean Hodgins and welcome back to this multi-part series on building your own Arduino-based neural network robot. In the first part, we took off-the-shelf components and built a custom prototype, and then we designed a custom circuit board. In the second part, we took that custom circuit board, added surface mount components, through-hole components, a bootloader, and then some firmware just to test it out. And now, finally, we'll be installing the neural network firmware and talking about it and making sure you understand how it all works. Let's get to it. So before we develop the neural network program, I've put together a really simple navigation program using the light sensors, but no neural network, just the light sensors controlling the motor. And I will break this program down so you can understand what's happening in each section. It uses the U8G2 library for the screen, that's what that's for. This include make logo is the very beginning make logo screen, that's all that does. And this enables the OLED. So all that stuff is just for the display. Then you've got photosensors, and then the motor outputs and the buttons. And then here, this is defining the analog inputs for those photosensors and enabling the buttons here. More OLED definitions, and then this is how the first logo is set up. You can look into that library. It's pretty simple once you understand it. That's just the setup, and then you can see here in the loop, it's just depending on what menu case is running, then it'll run that. So simple light avoid, that's the program that will make the robot navigate avoiding light, hopefully. In this simple light avoid routine, it reads from the 4 sensors, then it maps them from, you get a value from 0 to 1024 depending on how much light. But then it switches them from 400, because I find they still get light, to 0 to 48 for the top sensor and the bottom sensor, and then from 0 to 64 for the left sensor and the right sensor. It takes those values and it feeds them into something called draw ball dir, so it's drawing the ball direction on the OLED screen. So what this does is it takes those 4 inputs and then it defines them in X and Y coordinates based on how much more light each sensor has. So if the left one has more light than the right one, then the ball slightly goes to the left. And if the top one has more light than the bottom one, then the ball is going to move to the bottom one. It's kind of like a joystick on the screen, and that's what's controlling the robot. So once you have those X and Ys, those are actually sent to the motor control. Well, this is to draw that ball on the screen, and this is the motor control that will drive the 2 motors. So if we see in this motor control subroutine, I've defined the motors that 50 is not moving, 0 is completely backwards as fast as it can, and 100 is completely forwards as fast as it can. So what it does is it takes the Y offset and sets that as how much power each motor has, and then it takes the X offset, so the X coordinate, the left and right sensors, and then offsets that power from one motor to the other. If it's fully to the back sensor, then they would both drive straight at full power, but if they're slightly more to the right, then it would make it move to the left. So it takes that offset, sends it in, and then finally motor A and B, this is how you can control them. So you have a motor routine A where it takes the speed between 0 and 100, 50 being not moving, 0 being backwards, 100 being forwards. And that's how it defines it here. This is how it controls the motor driver. So it changes the phase of the input and then gives it a PWM input, depending on which direction it chooses. There's 100 ways you could do this, probably a lot of ways you could do it better than I've done it. This is what works. So it just keeps doing that over and over and over again. So let's see how that works. So you can see I've made a little menu here, but there's only one program on it. You can switch between them using the left button, but the other 2 just say blank. Anyways, if you go to the simple program, hit the right button to run it, then now we have a ball in the middle. Now the motors aren't connected at the moment. They've only got power when you have this switch that moves over. That puts power to the system from the battery, and they're powered through the battery. as you can see, it's pretty dead even right now because they all have the same amount of light. It might be a little bit to the left here because there's a little bit of a shadow on this one. If I put a shadow over this, then the ball moves up to the top. If I put a shadow over the back, then the ball moves back. And if you can imagine that being like a joystick, then you could see that it's going to make the robot move in those directions. So let's test it out. So now the motors are connected to the power source. We'll run the program. So as you can see, it's trying to stay in the shadow. But one thing we could implement is have it drive forward when it's fully in light. Let's add that right now. Okay, so what I just added is if the sum of all of the sensors is greater than a value, which would seem like they're all being lit, or it's not in a shadow, then it's told to just drive forward slowly until that's not the case anymore. So now we can see it's happy when it's in a shadow, not happy when it's not in a shadow. And it looks for the shadow as well. So as you can see, that program works really well, and it's pretty simple. It doesn't take that many lines of code to get the robot behaving the way you want it to. But it's not as cool as a neural network, and what's cool about a neural network is we can define certain extremes, and then it can work out the points in the middle on its own. So let's develop the neural network program now. So for the neural network, we're actually going to be adapting code that is found on the website robotics.hobbyscene.com. They have an Arduino artificial neural network, a really great example code that is actually designed to take a 7-segment input and translate it into only 4 bits. So you're taking 7 bits and converting them down to 4. It's a really cool, interesting program. But what we're going to be doing is we're going to take this set of code that they have, because they've developed all the math behind it, and then we're going to modify it so that it can run on the sensor inputs and then output to the motors. So we're going to be having this run continuously after it's trained to control the robot. It's pretty cool. So again, with this program written and everything modified, let's go through it and I'll explain everything again, and we'll just make sure you're familiar with everything that's happening within the program. We've gone over some of this stuff with the inputs. They're all the same. Now we have some variables that are for the neural network. We're going to define the extremes of the program. So the extremes of the inputs are going to be defined between 0 and 1, and 1 being the most possible light on that sensor, and 0 being the least possible light on that sensor. So here are the inputs. So here we have a matrix of 4 inputs by 16. So each one of these is the sensor input, and we're defining these now as the maximums. So as you can see, I've labeled them here on the right. So with this one, 0, 1, 1, 0, that means there's fully light on the left and right, but no light on the top and the bottom sensors. And we go through every possible scenario that we can think of that will allow it to properly learn how to behave, because we're going to correlate these with motor functions. And you don't actually need this many. You can experiment with removing some and then seeing how the robot behaves and how the behavior adapts to not having as many inputs. But this is what we're using. We've got 16 of the inputs, and these are the correlating outputs. Now, as I mentioned before, we gave the motors a value between 0 and 100. So now we've mapped that down to between 0 and 1, and these are the outputs to the motor. So when the left light is on and the right light has full light, then the motors are going to move. We're going to give the motors a value of 75 to drive forward, but not super fast. And as you can see, each one of these scenarios is kind of broken down. If there's light on the left, then have slightly more power in the left motor. and the right motor stationary. And then if we have light on the top, left, and the right, then we want the robot to drive backwards. So right now all we're doing is defining the extreme cases. Because we have all these extreme cases defined, there's going to be situations where they're not all fully light and not fully light. In fact, it's almost never going to happen. But what the neural network is going to do is going to define an equation that determines what the output of the motor should be and fill in all the gaps between all of these extremes. And that's what's interesting about a neural network, is that it can learn and adapt different scenarios just by training at these specific extremes. Up here we have some variables that I should explain. Pattern count, that's just the number of patterns possible for the training. Input nodes, we know we have 4 sensors, so we have 4 input nodes. Hidden nodes, it's kind of up in the air what you should do, but I always just do input nodes plus 1, and that seems to work for now. And you can always play around with these and see how it affects how long it trains, anything like that, because the training can take a while. Output nodes, we know we have 2 motors, so we have 2 outputs. Learning rate, that's the amount it's allowed to modify the weights between the nodes in the neural network. So the nodes are the inputs, the hidden layer, and the outputs. Each one of the neurons is called a node. And what you're doing is modifying the weights between them that are trying to get the output. So what's happening when you're training is you're taking the predefined outputs and the predefined inputs, as I showed you, and developing basically a very complex equation to make those two equal on inside of the equation. So it's going to go through all the training inputs and the outputs and make sure that they all work and they're very close to what they need to be. They're not going to be exactly 0.75 for the outputs if we tell it that, but it's going to try to get as close as possible. So it's going to start with a random set of weights between each connection, and then it's going to modify these weights every iteration of the neural network. So the learning rate is how much it's allowed to change those weights. And if it's too high, you will constantly have an increasing error or never find the proper equation. And if it's too low, it could take forever. And then if it takes forever, it'll give up as well. And then finally, success is the mean square error, which is basically it's trying to see how close it is to the inputs equaling the outputs. And that's kind of how you define when a neural network is trained. So once the success gets below the mean square error of this 0.0009, then we consider it trained and it should be able to operate properly. But you could increase this and see if it works, and you could decrease it to see if it works even better. It's not necessarily the perfect number here, but you need to play around with it and see what happens. So this is all part of the program that we took from HobbyZine website. So they explain it very well there, but basically it's a program that is checking. This is the training subroutine, train neural network. And this is basically their code that trains the neural network. What it does is it checks each time the error, and then it modifies the weight slightly, and it sees which direction it should increase or decrease the weights between each node. So all these are iterations for each node between the hidden layer and the output layer. And it does this iteratively, and that's what takes so much time, and that's why parallel operations on neural networks work really well. That's why GPUs are used for neural networks, because it can do a lot of small calculations at the same time. So the Arduino has to do each one of these on its own in each routine, which takes a while. And you can see it takes about 3 to 5 minutes. So it's checking each time, and this report every 1,000, I actually changed it to report every 100. And what this does is it outputs to the graph every 100 iterations of node changes to see what the error is. And once the error gets below that threshold that we define, the 0.0009, then it stops training. It's done. And all the weights have been saved in the neural network. So now that it's been trained, we can select the drive neural network function subroutine. What this is going to do is it makes sure that it has been trained. If not, it won't let you run it. And now, instead of the training set that we use, it's going to use our light sensors as inputs. So again, we read the light sensors. This time we map the light sensors to between 0 and 100 because it's an integer, and then we convert it into a float between 0 and 1. And those are now our neural network inputs. So we've got this routine, input to output, and it takes the 4 inputs that we just measured, physically measured from the robot. These 4 inputs are entered in, uses those inputs with the neural network and the weights to determine the outputs, and that is the output that you get from the neural network. And the outputs are the motor control. We end up with the outputs, with 2 outputs from the neural network. That gives us a value between 0 and 100. And then all we do is send those the same way we did before to the motors, and then because of that, the motors will be driven. And it will constantly refer back to the neural network, and it will constantly give you outputs. So let's train this neural network, and then we'll run it and see how differently it behaves than the other way. We've got 2 more items on the menu. So we've got simple, which is the one we ran before, which is still in this program. We've got train neural network and run neural network. Before we can run it, we have to train it. So when we do this, you'll see this will light up, and the graph will give you, every time 100 iterations goes through, the graph is going to display the mean square error. And it's going to make sort of a logarithmic curve as it gets closer to the value that we need. Okay, so now that it's trained, let's make the room really dark, and we can see if we can chase it around with a flashlight and see how it behaves. So that'll be cool. So all of these motor decisions are taking place based on the training data. So it works. Yeah, it works pretty well. It's trying to avoid the light and find places of shadows. Now if we were to train it again, it may behave differently, because each time you train it, the equation that maps the inputs to the outputs is slightly different because the beginning is random. So that's what's really cool about neural networks. Now you can also experiment with, like I said, removing some of the training inputs, have larger gaps between the extremes so that the behavior could be more erratic, or it doesn't actually want to avoid shadows. It could just drive around in circles. You know, anything could happen because it'll be less defined about the different amounts of light it could see. So why don't we try that again with the simple program, and we can see how that behaves in the shadow. You can see that the behavior is similar to the last neural network training. Now as you can see, a neural network is not exactly necessary in this specific type of robot. We were able to design a simple program that almost behaved the same way. But the interesting thing is to see the different behaviors that happen each time you train it. And also that you're not specifically giving it every scenario, but that it's defining the scenarios between the extremes within the neural network. And I think that's really cool. And you can adapt this to all different types of applications, and it's just a great tool to experiment with neural networks and see how they work. And you realize that they're not that complicated. They're basically an equation that is defining one set of parameters to equal another set of parameters. That's what a neural network does. So if you enjoyed this project and you want to build one yourself, head over to the GitHub. There, you'll find all the files needed to recreate the entire thing. It's fully open source. If you like this video series, hit that like button. And if you have an idea for something you want to see done in the future, leave a comment below, because I might be able to make it happen. If you want to check out my channel, I've got all types of projects that are fully open source, similar to this. They're pretty cool. You might enjoy it. Anyways, everyone, you know the deal. Be good. and have a good day. Oh, we lost a wheel.